Hello everyone. Welcome to the second lecture of this course. This lecture is on constraint optimization. So from this lecture onwards, I'll be mainly teaching on my iPad and writing down the notes. So if you find it a little bit slow, since the lectures are recorded, you can actually increase the speed from 1.5x to 2x. Uh, so you'll be able to properly go through the course. So, in this lecture, I'll be mainly talking about the meaning of optimization and the notations, feasible and the decent directions, KKT conditions, basically first order, and then some examples to show how you can solve these problems. So, note that optimization is a very vast field, and their entire course is dedicated to optimization. So this lecture by no means will cover all the techniques to solve constraint optimization. But however, the goal of this lecture is to introduce to you to this topic and introduce you to the techniques that we'll be using in this course to solve optimization. Right. So if you're interested, I'll link some YouTube playlists in the description down below. You can actually go through them and uh, increase your knowledge if you want to. So let's start with what is optimization. So uh, we can say that optimization is the act of making the best or the most effective use of the situation or resources. And typically most of the optimization problems are constrained because con- uh, uh, because constraint or the resources are always very constrained and always limited, and nothing is ever enough. So if you want to optimally use the resources, we need to do some sort of optimization, or we want to use effectively, then we need to do constraint optimization in general. So let us take an example. Suppose if I have some volume of water or some fluid V, and I want to put this water in a container, a cuboidal container, let's say, with the minimum amount of surface area, because we want to save the material cost, right? So suppose the box looks like this, and let L, uh, H and B be the dimensions of this cuboidal box. So if I want to minimize the surface area, I'll typically write it like this. So twice of L into B plus B into H plus H into L, which is basically the formula of surface area, subject to the conditions that L into B into H equals to V, which is basically the volume of water, right? And we also know that physically it's not possible to have zero or negative lengths, so we want positive lengths or positive dimensions, right? So typically this is how a constraint optimization problem looks like, right? This is the objective function and these are the constraints, right? Okay, so yeah, as I introduced above, this is how typically a constraint optimization problem looks like. This is called the objective function because this basically defines our objective, whether we want to minimize or maximize some function, right? So this is called an objective function. And we have certain constraints, um, some inequality constraints like hj function, and some equality constraints like EI function where j varies from 1 to L and I varies from 1 to M, and our X is restricted to some set S, so it belongs to some set S, right? So uh, we say that this particular set or the set formed by these constraints are either called constraint sets or we call it feasible set, right? And we assume that all the functions fx, hj of x, ei, all these are sufficiently smooth, right? And the feasible set is uh, which is basically this set, is given by set of all x's subject to x belongs to S and hj of x is less than equal to 0, and ei of x equals to 0 for all I belongs to 1 to M and j belongs to 1 to L, right? And we call this set maybe X, right? So the problem basically is we want to minimize f of x subject to x belongs to the capital X, which is the feasible set. Okay, so now let's talk about global and local minimas. Okay, so suppose if I want to say local minima, I'll say with respect to a function f in a way. So a point x star which belongs to some set X is said to be a global minima of a function f of x over x over capital X, which is basically the set, if f of x is always greater than f of x star for all x belongs to X. So basically what we are saying is that if I have a global minima, this will be minimum over all the x's which belong to my set X, capital X, right? Now how do we define a local minima? Local minima, as the name suggests, is basically minima over a certain region, in a way, a local region. So local, before we define what local minima is, let me define a neighborhood of X. Okay, so a neighborhood n of a n of x, basically I define it over some variable called epsilon. It's defined as this way, So for all z which belong to this particular set is called the neighborhood of x, right? So we call it epsilon neighborhood of x. So basically we call it an open ball, which is in the maximum epsilon distance from x is called the neighborhood of x. So suppose this is my point x. So all the points within the epsilon distance from x is called the neighborhood of x. Okay, so if the minima is over this particular neighborhood of x, epsilon neighborhood of x, then we call the point x star as the local minima. So a point x star belongs to x is said to be a local minima of fx of f basically over capital X, and for some epsilon greater than 0, such that f of x is greater than f of x star for all x belongs to the neighborhood of epsilon neighborhood of x intersection my feasible set x, right? And in both the cases, both in the case of global minima, if my f of x is strictly greater than my f of x star, then it is called a strict global minima. And similarly, if in this case also, if f of x is strictly greater than f of x star, then this is called a strict local minima. Okay, let's see an example. Suppose this is how my function f looks like, right? So this particular point is called the global minima because if you see, this is the global minima because at the value of f at this particular value is the least amongst the all the f of x's, right? So suppose this is my feasible set. So in this particular set, capital X, this particular point, let's say this is point 1, is called the global minima. Okay, and let's see some other point. Let's say this particular point. So as you can see, this particular point, it's smaller than all the x's in its neighborhood, say small neighborhood, right? But not obviously smaller than all the points in x, capital X. So we say that this particular point is the local minima. even so suppose suppose if I consider this point again, if you see, this point is also the like it's also a local minima. So all the so the point one is both the global as well as local minima, and point two, so call this as point two, is the is just the local minima in this case. Okay, so after we have uh, so we have understood the local and global minima, let's move to convex optimization problem. So convex optimization problem also looks like this. However, there are certain properties like my function fx is a convex function. My equality constraint function, which is ei of x, is affine. That is eix is of this form, ai transpose x plus bi, right, for all I belongs to this particular set. And my function hj is also convex function for all j belongs to, okay, sorry, it should be belongs to 1 to l. Okay, and this set S should be a convex set. So so then we say that the problem or the optimization problem is a convex optimization problem. So um, for people who don't know what convex set and convex functions are, I'll just briefly introduce you to this topic. So convex function is a function in which if you draw line between 2 points, then all the points on that particular line should lie inside this set. So suppose if I consider a set like this, right, and I take 2 points, uh, say this point and this point, right, and I start drawing a line which connects both of them, then all the points, since they don't lie on this in this set, so all the points on the line don't lie in this set, then it is not a this set is not a convex set. Okay, now suppose if I consider a circle and I consider any 2 points, say this, and I draw a line joining these 2 points, and we see all the points on the line also lie in this particular set, so this is a convex set. Okay, now like this is just a brief overview of what convex set is. Obviously you need to go through some more mathematical rigor, and whenever you go through a proper optimization course, you'll properly understand what convex sets and convex sets are. So now if I say, like, now let's see what convex functions are. So convex functions are functions in which basically if you uh, so suppose you choose 2 points in the set, say x1 sorry, and x2, and their corresponding value of the function at x1 and x2, fx2 and fx1. And if you join a line connecting these two function points, right, any point on this particular line should be greater than the corresponding x at that point. So suppose if I choose this particular point, this point is always greater than the value of the function at this particular x, right? So this is how you mathematically write it. Say lambda is greater than 0 but less than 1. We write this expression, and if this particular expression is greater than the value of x at that particular point, right, then this function f is a convex function. Okay, so this is a particular property of this special kind of function, right? Again, this is just, I'm just briefly telling you. You can actually, if you go through a course on optimization, you'll properly understand what convex sets and convex functions are. Okay, so now that we have seen what convex functions are, let's again see some example. So suppose I have this particular function which looks something like this, right? Is this a convex function? Obviously yes, it is a convex function because it satisfies all the properties of a convex function. Okay, and is this set from A to B, is this a convex set? Yes, because if we choose any 2 points, all the points on the line also lie in this particular set, so this is a convex set. Okay, so if we see this particular region, from, use a different color maybe, from this region to this region is the global minima. Okay, now let's take an example to visualize one more example, basically a proper example this time. So suppose if we want to minimize x1 plus x2 subject to x1 square plus x2 square equals to 1, and here x1 and x2 are obviously on the real line, right? So if I draw this particular so this is my constraint set. Okay, and I want to minimize x1 plus x2. right? So basically, according to what should be the minimum point, so a line which is going through this, so the value of this particular function x1 plus x2 decreases as we go in this direction, right? So the point which lies on the constraint set as well, in and also lies on this particular line, is the minimum point. So basically this is the x star, right? However, if you see, since like this is a equality constraint, you can actually just solve this and then put the, like you can solve it for one of the constraint and then put it in the optimization objective function basically. So suppose I want to substitute x1, so I can write x1 this way, right? And then I substitute this in the objective function. So I'll get minimize x2 plus minus 1 minus x2 square, subject to, so there is no constraint, just that x2 should be real, right? And obviously the constraint that x2 should be uh, x2 square should be less than 1, because if it is greater than 1, then this particular uh, like this particular inequality, this particular square root will be imaginary. So in this case, if we try to replace one constraint with another, we'll come up with a new constraint, right? However, we can still find some problems in which if we substitute the constraint in the objective function directly, we can reduce this constraint optimization problem to unconstrained optimization problem. So now let us reverse this particular example. I'll change the objective function to constraint function and constraint function to objective function. So suppose if I want to minimize x1 square plus x2 square, subject to x1 plus x2 equals to 1, given that x1 and x2 belongs to the real line. Okay, so if I just visualize this, in this case in this case these are the contours, right? I want to, so as I go inside, the value of the function decreases, and my constraint is this particular line maybe, right? So now I can find that this particular point which lies on this particular contour, this point will be the minimum, right? And if I just want to solve this, what I can do is I can just replace one of the variables in terms of others. So I'll just write x1 equals to 1 minus x2, and then I'll just replace it here. So my objective function becomes x2 square plus 1 minus x2 square, and there's no condition except the fact that x2 should lie on the real line, right? And if you solve this, then you'll get I think x2 is 1 by root 2 or something like that, or maybe I think it should be half. I think it is half. So we'll get x2 as half and we'll get x1 as half. So my x star, I mean the minimum in this particular case is half comma half. Right, so there are some problems which you can actually solve, even you can even solve them without using constraint optimization, just by replacing the constraints in the objective function directly. However, suppose if there are some inequality based constraints, there's no direct way to kind of substitute them in the constraint function directly. So anyways, we'll have to learn how to deal with constraint optimization problems. So that's all for this particular sub lecture. um, so I have actually divided the lectures into different sub lectures so that each lecture is not too big. Okay, so see you in the next sub lecture.